Well, good day, ladies and gentlemen. Welcome to our first lesson on chapter 10. I told you that we're going to hop right into this chapter right after the last section of chapter 9. And I always look forward to this chapter every year. It's a fun chapter. And yes, before we get too far into it, we will be doing math, okay? But it's going to be a little different circumstances. Obviously, we're going to be kind of toning it down a little bit just because I like to do a little more stuff in class. So the good thing about the math that you're going to encounter is a lot of it is formula driven. It's one of my favorite formulas, actually a favorite couple of formulas that we're going to be looking at in this chapter. And the other is just going to be some very simple conversions, okay? And I want to really show you how to do a couple examples with that. In today's video, we're going to be covering sections 1 and 2. The first section is about half a page long in your textbook, so I figured we can combine that with section 2, and we'll go from there. Anyway, Chapter 10 is all about gases. You wouldn't think that gases would be important enough to have their own chapter. Well, they are very important. And so we are going to discuss just how important they are to our daily lives and how a lot of their concepts associated with gases really impact quite a bit around them. So let's get started, all right? Anyway, we know some characteristics about gases already. We have talked about some properties of states, of matter, and so let's just kind of rehash those a little bit here. We can have situations where gases have different chemical properties, much like oxygen is going to support human life, nitrogen does not. But nitrogen is very important to plants, okay? Whereas, oxygen is released by plants. So again, very different in terms of their chemical properties, but they still behave quite similarly in their physical properties. Unlike liquids and solids, gases are able to expand and fill their containers. They are highly compressible and have extremely low densities. Okay, so more characteristics of gases. Two or more gases form homogeneous mixtures regardless of identities or relative proportions of the gases, meaning they're going to be the same. Okay, they're going to be the same throughout their mixture, no matter what identity they have. Liquid water and gasoline. Imagine putting those two together, okay, or liquid and oil. When we try to mix those two substances in liquid form, they do not mix at all. Okay, we see that example in oil and vinegar salad dressings. Okay, however, going back to water and gasoline, they will have vapors that will exist right above both their liquids, okay? When those vapors, which are gases, when they are near each other, they will mix, much unlike their liquid relatives. And the reason why we can have water vapor and gas vapors create a homogeneous mixture is because the molecules themselves are relatively far apart. And so when we look at liquids, they're much more compact and closer together. But when we have all this, quote unquote, empty space between the molecules, they really don't interact a whole lot. So, excuse me, they are able to form these homogeneous mixtures. Excuse me. Now, when we talk about gases, one thing we really need to investigate and take a look at and take into consideration is pressure. Now, pressure is the amount of force applied to an area, and we can calculate pressure by taking the force divided by the area. And atmospheric pressure is what we're going to be kind of looking at here when we deal with gases, is the weight of air per unit area. So if you look here, if we take a 1 meter by 1 meter column of air, it's going to have a mass of about 10 to the fourth kilograms. And again, depending on where you are located on planet Earth, if you compare from where we live right here to Denver, Colorado, somewhere around here, okay, we talked about differences in their altitudes above sea level. Well, since Denver, Colorado is higher in altitude, it actually has a much smaller air column that is going to be weighing down on the residents of Colorado. So, therefore, your altitude in comparison to sea level is going to kind of determine how much air pressure you experience. Now, we're going to be looking at quite a few varieties of air pressure units. If you have a bike pump or any other type of pump at your house, you might actually see, if it has a dial on there, a couple of these different types of units. Pascals. Okay, 1 Pascal has an equivalent of 1 Newton per square meter. We have bar, which is 1 bar is equal to 10 to the 5th pascals, or 100 kilopascals. Now, bar, if you watch the Weather Channel or your local news channel and their weather segments, bar is dealing with barometric pressure, okay? That's where we kind of get that. That's the relationship we see, okay? Now, other units of pressure. We have other units of pressure in terms of millimeters of mercury or torr. Now, millimeters of mercury and torr are kind of a 1-to-1 ratio, okay? Really, the only difference is the name, okay? The numbers will equal each other, and so if you have to convert between millimeters of mercury and torr, all you have to do is change the label. And millimeters of mercury or torr, really, they get their values based on the differences in the heights measured in millimeters of 2 connected columns of mercury. So if we look here, we have a column of glass tube that has mercury in there. That bottom open part of the tube is submerged in some pool of mercury or a bowl of mercury. As pressure increases on this pool of mercury, it actually forces the mercury up the tube. And so the higher the mercury is up this tube, the higher the pressure is in the atmosphere. As pressure decreases in atmosphere, it provides less pressure on this pool of mercury, allowing for this mercury to go on down the tube, okay? Another unit of pressure is atmosphere. 1 atmosphere is equal to 760 torr. Again, that number, 760, comes from a standard that was used a long time ago of 760 millimeters of mercury, which again equals 760 torr. But this is really the all-important slide right here. All of these are pressure equivalents or pressure conversion. So in the past, some students have had a little trouble understanding what this slide means. Really, anytime you have to convert between units, you're going to be using these values, okay? So 1 atmosphere is equal to 760 millimeters of mercury, which is 1 atmosphere is also equal to 760 torr. 1 atmosphere is equal to 1.01325 times 10 to the 5th pascals, so on and so forth. But each one of these values is equal to the others, okay? That's how we're going to use this particular slide to help us with our conversions, okay? Everybody, each one of these values, again, is equal to anything else on here. So make sure you put a star, highlight, whatever you need to do on this slide, because you will be referencing this for quite a while, all right? Let's look at some examples of conversions. I know this is your favorite thing, so guess what? You're going to need your calculators out for this. So first, we're going to do a couple of example exercises on here, and then we'll look at the practice questions on the next slide, and we'll see where you stand on this, okay? So, see if I can get my lights right here. So, for part A, we are to convert 0.357 atmospheres to torr. Okay, again, we know atmospheres and torrs have a relationship. So what we're going to do, we're going to come on down here. With any type of problem that we've done throughout this year, the first thing you always write is the given. And the given in problem A is 0.357 atmospheres. So we write that first. We then use the conversion factors from the previous slide to help us transition from atmospheres to torr. So the conversion factor is 760 torr is equal to 1 atmosphere. And since our answer needs to be in torr, that 760 torr goes on top, atmosphere goes on bottom. Atmosphere labels can cancel out, leaving us with the label of torr. So we take 0.357, multiply by 760 to get 271 torr. That's it. That's it for that question. Next, convert 6.6 times 10 to the negative second torr to atmospheres. Same process. Write down what you're given. Then use the previous slide to look at the conversion factors. So we need to go from torr to atmospheres. So 1 atmosphere gets placed on top. 760 torr gets placed on bottom. Torr labels cancel out. And then we take 6.6 times 10 to the negative second, multiply by 1, divide by 760, and we get 8.7 times 10 to the negative fifth atmospheres. Really, really small pressure. Lastly, convert 147.2 kilopascals to torr. Again, that's our given. So we write 147.2 kilopascals. On the previous slide, again, we're transitioning from 760 torr. So we still put 760 torr because 760 torr is equal to 101.325 kilopascals. That's the conversion factor. Okay, make flashcards. I don't care what you have to do. Get those numbers down. So 760 torr goes on top. 101.325 kilopascals goes on bottom. Kilopascals cancel. Take 147.2 multiplied by 760. Take that answer, divide by 101.325, and you get 1,104 torr. All right. So there's our 3 examples, 3 practices of converting. Now let's look at some sample problems, okay? All right. So, see if I can get this in line here. Sorry, always transitioning my lighting here to hopefully allow you to see it a little better. Because from my angle that I'm looking at, it looks a little dark, but then I change and it looks like it should be okay. Anyway, so in countries that use the metric system here under practice A, atmospheric pressure in weather reports is given in kilopascals. Convert a pressure of 745 torr to kilopascals. Okay, well, let's start off. What's the first thing we always write? It's going to be the given. So 745 torr. Okay, we're going to multiply that by the conversion factor. Again, going a couple of slides back on the equivalent pressures slide. Excuse me. Their equivalent pressures of 101.325 kilopascals is equal to 760 torr. Again, I put torr on the bottom because that needs to cancel out. So I have it set up to where my answer will be kilopascals. Torrs cancel. So I take 745, multiply by 101.325, and then take that answer and divide by 760. If you wanted to put this in your calculator, now's your opportunity to pause the video to see what you get. And then once you've calculated it, written it down, restart the video, hit play, and check your answer. So go ahead and pause if you haven't already done so. All right, if you're just coming back now, the answer you should get is 99.5 kilopascals. So hopefully you got that. If not, go back, start over. It's a quick calculation. Excuse me. Next question. B. Now I'm going to take this a little bit longer. I'm going to show you the baby steps. You know how I like to show baby steps in a lot of these calculations here, just so you see every single step. And if you get to a point where you're comfortable and you can find a shortcut and it still comes up with the right answer, by all means do it. But I am going to do the baby step method. So the pressure at the center of Hurricane Katrina. Some of you were just wee lads and lasses when that came out. That was in 2006, 2005, 2006. I can't remember now. It's been so long. But anyway, a while ago for most of you, if not all of you. So the pressure at the center of the Hurricane Katrina was 902 millibars. There are 1,000 millibars in 1 bar. We need to convert this pressure to atmospheres. Okay, so we don't really have millibars at our on our equivalent pressure list. So what we're going to need to do is convert the millibars to bars, which bars and atmospheres do have a conversion factor for each other. So we're going to add a step to this. So again, like any other time, write what you are given, 902 millibars, okay? We're then going to first convert millibars to bars. And it says right here, there are 1,000 millibars in 1 bar. Well, we need to take the step to get to bar, so that goes on top. And 1,000 millibars goes on bottom. That way we can cancel out those units. Okay? So I'm not going to calculate between every step here. I'm going to show you the steps. And if you want to, you can calculate this step and then go to the next step, whatever you want to do. But I'm just going to go in one string here. Okay? So now that I'm at bar, I know that I can transition between bar to atmospheres. And so my answer, I need to have atmospheres. So looking on that equivalent pressures list, we know that 1.0 atmospheres is equal to 1.01325 bars. This allows for bars to cancel. Everything's canceled except my atmosphere label. And so again, you can pause the video right now to go ahead and calculate that. And then once you've got it calculated, you can hit the play button and check to see what you got. All right. So after you've calculated this whole string, you should get an answer of 0.890 atmospheres. Now that is significant, okay? Having this low of an atmospheric pressure. And then we're actually going to discuss some weather here in just a few minutes, but we'll come back to that in just a short while, okay? So again, your book, if you want more examples, your book has, you can always go back to the problem set questions in the back of chapter 10. You could look through the sections and see others in practice if you want to. But yeah, converting these units are pretty straightforward. All right. Now, another thing that measures pressure is what's called a manometer. And the manometer is used to measure the difference in pressure between atmospheric pressure and that of a gas in a vessel. There is a wide variety of manometers used throughout the world in various professions. Now, a very simple drawing of a manometer would look like this, where we'd have a vessel with pressurized gas in this kind of a U-tube shaped glassware. And some of these are open at one end, some are closed. So you just have to pay careful attention. And the ones that are open, those are exposed to atmospheric pressure. So these allow us to determine atmosphere pressures. Others, like I said, can be closed here, and you kind of go a slightly different route with those. But really, the main thing is we measure the difference in the height between the top of the column here and the top of the column here, okay? If this side of the column is higher than this side of the column, that means the pressure of the gas in this vessel is not as large as the pressure of the atmosphere. However, in this case, we see that the height of the mercury or the liquid, or gas even in this, usually it's mercury, since on the right side, the side that is open to the atmosphere, is higher than that of the gas side. That means that the pressure of the gas in this vessel is actually greater than the atmospheric pressure. And also, with that same thought, if they're equal on both sides, well, that would mean that the pressure in the vessel is the same as atmospheric pressure. So that's one way we can do it. Now, in years past, we've always, looked at manometers and have done calculations with manometers, but it's one of those things that I just really prefer to look at and calculate in class, okay? Because we do it quite a bit in class, and it's just, for me, it's easier to do that, draw it on the board, and do all that. So we're just going to discuss manometers here. And again, if you have more questions about manometers and how to calculate it, by all means, contact me, get a hold of me. But we are going to just discuss and kind of leave the calculations for later years. Now, as I said, manometers have quite a variety of uses for various occupations here. Manometers are used to obtain precise measurements of the pressure of gases in lab experiments. In medicine, a sphygmomanometer measures blood pressure. So if you've ever been to your doctor's office and they've put that black cuff on there that seems to cut off all circulation to your arm, or if you've seen somebody who's had that done to them, that's a sphygmomanometer, and that measures pressure as well. In engineering, they have aqueducts, bridges, and even swimming pools that a lot of times will be used to measure the pressure of water that is being exerted onto the structure. So again, these are just some examples where we see manometers used. Now, like I said, we're just going to bypass the calculation of manometers and how they measure gas pressure. Instead, what we're going to do is talk about a few things that are going to lead us, or at least this standard pressure, this idea of standard pressure is going to lead us into our next sections throughout chapter 10. Then I want to talk about weather just briefly. We are in springtime, and the weather can't make up its mind, it seems like. We've got snow one day, 70 degrees the next day, and then rain for 3 days. So just a real brief discussion on pressure and weather seems appropriate. Anyway, the idea of standard pressure, we've got to be thinking about when we are talking about later sections in this chapter, okay? Normal atmospheric pressure at sea level is referred to at standard pressure. So that means that standard pressure is 1 atmosphere, but it's also equal to 760 torr, or 760 millimeters of mercury, or it's also equal to 101.325 kilopascals, or any of the other units of pressure that we saw a handful of slides ago on that slide, okay? So all these values, as well as the ones listed on your pressure equivalent slide, those all represent standard pressure. Everything that comes at sea level, basically, okay? Now, a little note of weather and pressure. When you hear the terms low pressure, that means the air in our area is warming. It's starting to rise and then cool, and then we start to see the formation of clouds. Usually when we have low pressure, we see the association with rain and wind and thunder, and it causes a pressure gradient. And so we tend to see somewhat windy weather. When we have low pressure, it's a little windier, and this air that's warming is causing the air to rise. And a lot of times when there's warmer air, there's also more moisture. When moisture rises and cools off, it condenses. That's when we start seeing a decent rainstorm. Again, it causes a pressure gradient. Everything likes to be in balance. So because of this pressure gradient, it causes air to be moving real close, real fast towards that area. High pressure, we have cooler air. And the air actually will start to sink so it can warm up. And so a lot of times we'll have nice weather associated with high pressure. Okay. We can have snow come as long as we have high pressure, if the weather has been frosty. So air pressure does contribute a lot to our changing weather patterns. So right now, as we see, we're in the midst of spring here, and we are having the sun being at a new angle, and we're starting to get more sunshine, which is going to cause it to warm up. And then, of course, the warm air, as we just said, is going to rise, and we're going to have some more moisture in the air. And we're also getting moisture from the Gulf of Mexico that's blowing up here on jet streams, and it's forming clouds and can have prolonged and somewhat strong. We're starting to see a lot of tornado activity here, especially the southern part of the United States, because the drastic changing in the weather. And of course, now that we have this new fluctuation of air temperature, it's causing pressure gradients. And you notice that it tends to be a little more windy in the springtime, because we are creating those pressure gradients, and we're causing air to move into the area to try to get a balance going on here. So anyway, pressure, we're dealing with it, and we're also experiencing it in our own lives. So that's going to be it for sections 1 and 2 of chapter 10. Starting in our next video, we're going to be looking at gas laws, and we're going to look at some individuals who really dedicated their lives to studying gases and pressure, and then we're going to look at how their ideas and their studies and how we can calculate that, again, in some very simplistic formula-based calculations. So until then, stay safe, stay healthy, and I will talk to you later. Bye-bye now.